Alright, so the next few chapters should be pretty interesting for us here in chemistry, but we're going to give it a go anyway. We're going to be starting chapter 8 here. Your objectives for this first section are to list 3 observations that suggest a reaction has taken place, write a word equation, a formula equation for a given chemical reaction, and balance the formula equation by inspection. Right, so a lot of things that we're going to have to practice. There's also a lot of things that you're going to need to see, some examples of reactions. I may be posting extra videos that'll show you what, say, like a precipitation looks like, right? So examples of these things that we're talking about so that you can use that and build off of that. But at the same time, there's going to be a lot of work that's done that you're just going to have to practice and just going to have to get good at, and it's going to be hard to do that. Right? You're going to have questions at times. So make sure that you don't hesitate to email me. Right? I'm going to post resources, lots of things to help you learn how to balance equations, things like that. But I can only do so much, right? If you don't ask questions, you will probably struggle. So make sure that you keep up with things and you do the best that you can, right? When you're turning in work and I'm seeing what you're doing, I should be able to tell what's going on, what's going wrong. So don't be afraid to just post it as is, right? That way I at least know where you're at and I can help you the best that I can. So I'll try to be a little bit flexible. I'll return that thing, let you redo it, get a better grade a lot of times. That way you can actually figure out how to do it even if you can't figure out a way to ask a question. So just bear with me. We'll do the best that we can. So anyway, our first thing in these notes, and by the way, you should already have these notes. I did post them so that you could print them out, but if not, you can just use scratch paper. Doesn't really matter, right? You just have to have it some way, somehow. But chemical equations use symbols and formulas to represent these different things that are reacting, these reactants and products in whatever the reaction may be. So it's going to look a little something like this, right? I can react hydrogen gas. So I might not just put hydrogen, but also put the state behind it in parentheses. That G just means gas. Right? React hydrogen with oxygen. If I heat those, if I ignite those 2 reactants, I can make a product. They burn to make water. Right? At higher reactions, it's likely that water would be a gas state, but this is an example of a reaction. This is a chemical equation. I give you all things with symbols. Right? But then I should also balance this so that there's the same amount of each thing on both sides of the equation. Right? So when I come back through, and that's another little thing that we just kind of pick up on, and you just learn a little bit at a time along the way. We may have talked about it before, but hydrogen and oxygen both are diatomic in nature. Right, so when that single element's all by itself, right, there might be more than one atom of that element, but when you have that single element all by itself, it's usually diatomic, right? So hydrogen's going to be like that. Nitrogen's also going to be like that. Oxygen's going to be like that. Any halogen will be like that. Whether it's fluorine, chlorine, bromine, iodine, all 4 of those things would usually be diatomic in nature. So again, if you want to put that on your periodic table in your planner, put a little 2 with Sharpie next to each of those things, right? You have to remember to do that because in an equation, it's always going to be a diatomic oxygen. It's not just going to be a single oxygen. If you don't do that right, you're not going to be able to balance things appropriately. So lots of little details come into play. We have to be able to do that correctly because otherwise, to balance this, I need 2 oxygens on the right to go with the 2 oxygens on the left. And now I have 4 hydrogens on the right, so I need 4 hydrogens on the left. This is what my balanced chemical equation would look like. Again, we'll work our way up to building something like this and be able to do this very well, hopefully in the future. But those little things are necessary. I do need to know that it's a diatomic hydrogen, not just a single hydrogen. I do need to know what state those elements are in. They might all 3 be in the same state this time, but in the future they won't be, right? So Chemical equations, we're going to learn how to use those. Reaction indicators. How do we know that a reaction has taken place? Right? Usually I would come up with all these examples just in a conversation with you guys, but since obviously you're not here, I just have to go through them. So the first three you probably would be able to guess, right? If you want to pause right now and try and guess as many as you can, that'd be a great idea. But the first three you'd probably be able to come up with. Because the first one is evolution of energy and heat is light. Right? You know this when you look at fire, right? When you burn something, when you combust something, that's a reaction. And energy, lots of energy is released in that reaction. And you can also see the light that comes from it too, right? So evolution of energy is heat and light. That's an obvious reaction indicator. You can also have the flip, right? Now there's no opposite of producing light, but sometimes reactions feel cold, right? Because they suck in energy from their surrounding. So you can also notice that as well. But typically, if you're going to notice it, it's this situation, because most spontaneous reactions in nature are exothermic. So they would release heat, not absorb heat. So there would be other examples, but this is the first indicator of a reaction. The second indicator would be a color change. Right? If you see a new color, that had to have indicated that there was a change in your substance, right? Because now it's refracting light differently, it's reflecting light differently, whatever it happens to be, right? So color changes, definitely indicators of reactions. So you know that the Statue of Liberty is made of copper, but it's certainly not copper colored. That's because it's reacted, right? The surface of that statue itself has rusted and now looks green, because that's the color of copper oxide. Production of a gas. If you see bubbles, that's definitely a reaction, right? So you created a gas where previously there was just a liquid, or things dissolved in that liquid. That's going to be a pretty obvious reaction indicator. But there's another one that you may or may not be familiar with. You can also produce a solid in a liquid, right? So if you have these precipitates that form and actually sink to the bottom of the container, right, that's one of those things I'm probably going to have to link. I'll link a couple of example reactions so you know what it looks like when a precipitate is formed. Right? But if you create a solid where previously you just had liquids and or soluble reactants, that's going to be a precipitate. Okay, then we get into law of conservation of mass, things you've done before, definitely in physical science. This is where that coefficient comes into play, how we balanced that chemical equation before. So remember, it wasn't just one hydrogen, it was two hydrogen molecules and one oxygen molecule to make the two waters when it was all said and done. Again, in this case, maybe I'm not showing my, excuse me, that pen went weird on me. Maybe I'm not showing the states, because it's not always necessary to show the states. But I definitely have to have the relevant number of each thing. Right? There's definitely a 1 here, even though I don't normally write that. But there's one oxygen, two hydrogens that react together to make two water molecules. Word equations. Obviously, you have your reactants and products represented as words. So as methane and oxygen react to make carbon dioxide and water. That same equation is represented below as a formula equation, right? So methane happens to also be called a name that you would know, carbon tetrahydride, which is where this formula comes from. Oxygen is diatomic, like we said before. Carbon dioxide, 1 carbon, 2 oxygens. Water is H2O. We're pretty familiar with that by now. I didn't have to tell you that it's dihydrogen monoxide up here. But this formula equation represents those reactions and products with symbols and formulas. Again, that's what we're usually going to have. But if a equation is described in words, you're going to have to figure out a way to write a formula equation. But this still would need to be balanced. Again, you have to follow that law of conservation of mass. If there's 4 hydrogens on the left side, there better be 4 hydrogens on the right side. So I'm going to use a 2 coefficient. 2 coefficient. 2 times 2 gives me 4 hydrogens total with 2 waters, right? But then the oxygens aren't balanced. But I do have 2 oxygens in the carbon dioxide and 2 more in the water. Again, the coefficient goes to both things, not just the hydrogen, but the oxygen as well. 2 water molecules, there are 2 oxygens. That's 4 total on the right. So I need 2 oxygen, diatomic oxygens on the left. 2 times 2 is 4. Otherwise, the carbons are balanced and everything else is balanced, so this should be good. When I'm balancing equations later, right? Again, remember, 1s are never necessary, so I could just leave those blank. But sometimes when I'm balancing, I like to put in the 1 if there was a blank provided, just so I know that I'm done balancing that equation, right? This is like an indicator when I skip over some other ones later, which ones do I need to come back to and do, right? So we'll learn how to balance appropriately. It's usually just as simple as what I just did, right? And sometimes it's just a trial and error situation, right? It's not an easy thing to learn, not an easy thing to teach. It's just something you figure out through experience, usually. So I'm going to give you some resources for that later. Other symbols that you need to look out for in reactions and equations, right? Obviously, you saw the yield symbol. That arrow just tells you you're producing these products. They came from the reactants. But a lot of times, that arrow will have 2 heads on it, right? It's actually a reversible reaction in that case, which means that you can form these products, but those products could actually be reacted again to reform the original reactants. Most reactions are actually reversible. We like to think of them as just being, as just working in one direction, but they are typically reversible. Again, sometimes they'll draw the arrow like this, but it would mean the same thing. If it's pointing both directions, that means it's a reversible reaction. And there may be some kind of equilibrium that goes with that. Otherwise, other symbols that I've already started using, right? I could indicate the state of matter, right? So solid, liquid, gas. There's a 4th state of matter that you may or may not be familiar with. So this AQ actually means aqueous. So you might need that in your notes. And aqueous means that that substance is dissolved in water, right? So you might want to add that in your notes too. Otherwise, other symbols you're going to run into, you have your yield arrow. A lot of times there's going to be a symbol over the top of the arrow, and you're going to need to know what that means. I already used this one in the notes, right? This just means that I heated those reactants before I could make those products. I had to add some energy to get things started. I needed a spark to get that fire going, that combustion going. Otherwise, there's lots of different things that can be over the top of the arrow. Whatever it is, it's a condition that needs to be met. It's possibly a catalyst that needs to be in place in order for that reaction to occur. So there's lots of different examples you can have. There could be a specified pressure, right? Maybe you have to have 2 atmospheres of pressure to make this reaction work, which is double normal atmospheric pressure, right? 1 atmosphere is what you're experiencing right now, right? But maybe it's a specified temperature. Maybe it only works at 0 degrees Celsius. Maybe it only works at 451, right? So specified temperatures. Sometimes there's another chemical, right? This was an example they used in the book, manganese dioxide, right? So sometimes you have a specific chemical that's present that acts as a catalyst that makes this reaction work. So if something's over the top of an arrow, it's either a condition that needs to be met, like a pressure, temperature, that kind of thing, or it's a catalyst, like that manganese oxide. These are described reactions. Again, I told you that you're going to need to be able to take these word equations and turn them into formula equations. You need to be able to put this in formulas. So hydrogen peroxide, you guys should remember what that looks like, right? H2O2, it looked weird, remember? Hydrogen peroxide that's in an aqueous solution. So I should put an AQ behind it. Decomposes to produce, as soon as you see that to produce, that's your arrow, oxygen and water. Oxygen, again, is always diatomic. That's something we have to remember. So if I just put a single oxygen here, I'm going to be wrong. I'm not going to be able to balance this appropriately. That oxygen, I would guess, since it didn't say anything, is a gas, because this would probably be near room temperature. Whereas, water is typically a liquid at room temperature. So I can put in states for all those things, right? Even if I have to assume some here and there, right? Otherwise, if the state's important, I would tell you what it is every time, right? Otherwise, these are just my symbols, my formulas. Right? I also have to balance those things. Right? So I look back and forth. I have 2 hydrogens on both sides, so that should be fine. But I have 2 oxygens on the left, and I have 3 oxygens on the right. Both products have oxygen in them, so I have to account for both. Problem is there's an odd number of oxygens on the right, so what I know to do here is actually double the water, because that makes it an even number of oxygens on the right. Then I know I can create even numbers on both sides. What I did was create 2 oxygens here, 2 more here, which makes 4 total. So 2 times 2 gives me 4. So I know I need 2 hydrogen peroxides to create 1 oxygen, 2 waters. Hydrogen and oxygen are balanced on both sides. So again, that's something that you're going to learn how to do, how to balance these things appropriately, but it may take some practice. The second equation here, solid copper metal reacts with aqueous silver nitrate. Which again, I may have to post some resources later, but you could easily look up this reaction on YouTube and you're going to see a lot of cool things, right? But copper reacts with aqueous silver nitrate to produce solid silver metals and aqueous copper nitrate. Copper and silver, unlike hydrogen, oxygen, nitrogen, whatever else I said, they are singular when they're just all by themselves. So I just have 1 copper there. I just have 1 silver on the right. But then when I do a copper 2 nitrate, remember, because it's a copper 2 nitrate, I'm going to have 2 nitrates to go with that plus 2 copper ion, because nitrate has a -1 charge. So again, you got to make formulas that are appropriate. Again, I'm forgetting my states here. This is solid, this is aqueous. Hopefully I'm not running off the slide, what you can see. But otherwise, I need to balance this appropriately. And now that I have 2 nitrates on the right, don't think of it as separate nitrogens and oxygens. If you see nitrates on both sides, that's what you're balancing. There's 2 nitrates on the right, so I need 2 nitrates on the left. But that means I need 2 silvers on both sides. Otherwise, this is now balanced, and this could be my reaction. So again, you just kind of figure it out as you go, but taking this described reaction and turning it into a chemical formula is important. Solid zinc metal reacts with aqueous copper 2 sulfate to produce solid copper metal and aqueous zinc sulfate. Maybe try that one on your own. Just pause the video for a second. Okay? I'm going to do it, obviously, because I can, and I need to, and you need to check with me. But if you pause real quick, you could definitely try this yourself. Solid zinc reacts with copper 2 sulfate. It's a 1-to-1 there. They both have 2 charges. Again, it's aqueous, so I put the AQ. They react to form solid copper. And zinc sulfate, also a 1-to-1. Since they both have 2 charges, +2, -2. Again, this would be aqueous. I gotta balance it appropriately, but luckily enough, it is all balanced already. There's 1 of everything, essentially. I know there's 4 oxygens, but there's 1 sulfate on both sides. Never think of the oxygens and sulfur and sulfate as separate things. If it's sulfate on one side and sulfate on the other side, you can usually just balance it straight up. So be able to do that anytime it's necessary. Otherwise, there's lots of balancing examples on this slide. This is where I definitely need you to hit pause and try to balance all these things. I'm going to go through and do them, like I said, but you need to figure out how to do this for yourself. Some of these are easier than others, but I'll walk you through step by step what my thought process is so that you can maybe figure it out. Otherwise, a lot of people like to, say like in this first example, they like to keep track of each thing. The zinc, what was it? Oxygen and carbon separately. Because essentially I have this zinc oxide, a carbon, and zinc and carbon dioxide. I'm trying to balance this, right? And if I just look, I have one zinc on both sides, so I'll just do tallies for that, right? And I have one oxygen on the left, two oxygens on the right. I have one carbon on the left, one carbon on the right. So I can see already what's not balanced, the oxygens, right? So I need two oxygens on both sides. But every time you add a number that's not a 1, you change stuff, right? Not only did you make it two oxygens on the left, but you also made it two zincs on the left now, right? So the next thing you need to balance is the zinc, right? Again, I could put a 2 over here. That only affects one thing. Now everything is balanced. That first one's actually fairly easy. But sometimes you need to keep track of each element or each thing, because you could also, again, balance sulfates as a thing, or nitrates, or whatever else you recognize to be things that we learned before. But whatever you need to do, you need to be able to balance these things, right? So again, I just finished that first one. You could pause and figure out the rest of them. Again, I don't have the right ones, but I'm going to do it anyway. Now I'm going to go through and do the rest of these, but hopefully you've already tried them. So the second one actually is pretty tough, but first thing I would look at is possibly a hydrogen, right? So I see two hydrogens on the left in the water, so I need 2 over here. I'll put a 2 in front. So now sodiums are the same on both sides. That's good. Oxygen, I have 6 on the right. I have 1, 2, 3, 4, because oxygen's in everything on the left. So you got to be careful about that. That gets kind of confusing, right? So I'm going to have to get an even number 6 on the left over here, and that's not currently possible, because no matter what I do, I'm going to throw off something else in the process. So I need to understand that sometimes you just have to be creative. You have to figure out a way to make this work, right? What I'm probably going to want to do is go ahead and double the one thing that I did. Unless I'm screwing this up majorly. Sometimes I do that too. If I do 4 there, then I can have 2 here and 2 here, because sodiums and hydrogens would still be balanced. And then I'd have 6 hydrogens on both sides, or 6 oxygens on both sides, but it doesn't balance. See what I mean? Sometimes you start going through it and you're screwing it up just like I just did, and that's just the way it is. It's trial and error. You will figure it out eventually. It can be difficult. Right? Now, what I was missing the first time that I just realized was that when I put a 2 over here, there's actually 2 carbons. So I actually needed to put a 2 here, which actually makes 6 oxygens on the left and 6 oxygens on the right. So I just overthought that one and screwed it up. Same thing you're going to do sometimes. So just do what you got to do. Next one with the nitrogen dioxide, water, nitric acid, nitrogen monoxide. Let's see how to do this one. I try the hydrogens first, the 2 here. Then I'm going to need 2 nitrogens. That should give me 5 oxygens on the left. 6, 7 on the right. So that's not going to work out very well. Although, just realized, again, I have 2 nitrogens here, but I have 1 nitrogen over here too. So I screwed that up. I need a 3 here. That might change things. Now I have 6 oxygens here, plus 1 more here, 6 oxygens here, plus 1 more here. This should be balanced. So again, sometimes they're tricky. You just got to think your way through it. That should be balanced now. Next example. Right, if you see oxygen on both sides, there's 3 over here, there's 2 over here. Just use the least common multiple. 3 of these, 2 of those. Now I got 6 on both sides. I will have to complete that by having 2 potassiums and chlorines on both sides. But this one should be balanced now. Next example again, I'm going to consider sulfates as a thing, so I got 1 on both sides. I got 2 hydrogens on the left, so I need 2 hydrogens on the right. 2 chlorines on both sides, 1 barium on both sides. This should be balanced already. So we'll try to make it more difficult than it is. It's pretty simple. Aluminum oxide and sulfuric acid react to make aluminum sulfate and water. I can see sulfates on both sides, so I might balance that. I had 3 here, means I need 3 there. That gives me 6 hydrogens right there, and I multiply 3 times 2. So I need 3 waters to get 6 hydrogens. And that means I have 3 oxygens for both sides. You ignore the oxygens and the sulfates. And I have 2 aluminums on both sides. This should be balanced. 1 and 1. Last one, sulfate. I got 3 on one side, 1 on the other side, so I'll probably just put a 3 here. That means I have 6 lithiums, but 2 aluminums on both sides. This should now be balanced. Again, that can be difficult to do. Notice that I made some mistakes along the way. You just work your way through it. Again, I'm going to post a resource for balancing specifically. You definitely need to do that. In fact, I'm going to create an assignment where you should maybe screenshot and post that screenshot to show me that you did it. Because it's a simulator that you can do online. You can do it on your phone. Right? So we're going to have to be creative. I'm going to create some resources, post some resources. I'm also going to post a schedule, right, with what things I think you need to be doing every day. I'd like you to follow along with that schedule. It will also have some deadlines, some due dates, but I can be flexible with those if you contact me. If you tell me, hey, I can't get that done, I can't figure this thing out, right, then you can definitely have some extended time. I know this is going to be difficult. But don't be afraid to ask questions, send me emails, and look things up for yourself. Find these reactions online, see what they look like. It'll be interesting.